Hello, and welcome to the Floating Tape Lab. In this lab, two charge tapes are created and we need to determine the excess charge present on each of them. The purpose of the lab was to conduct an experiment in which the approximate excess charge on a piece of clear tape could be measured, along with using a distributed charge model. The fundamental physics principles at work here include the point charge model, which is described by Coulomb's law, in which the E field equals K times Q over R squared, and that can be transformed into a force by multiplying it by another Q. The force of gravity on an object near Earth's surface is F equals mg, and superposition, which is seen in the figure in the top right, where multiple individual fields can be combined into one larger net field. In this lab, the approximate charges of the tapes were found. The magnitude of the electric force is found to be 5.131, that's 10 to the negative 4 newtons. The magnitude of the gravitational force was 2.06 times 10 to the negative 3 newtons, and the difference there is going to be discussed later. And that the final charge of the tape was found to be 1.367 times 10 to the negative 8 coulombs. Assumptions that had to be made was that each piece of tape had the same charge. The distributed charge will be used for the calculation, dq, that's the tiny bit of charge in each individual point charge that we are calculating with. And that overall each tape is negative, and that air resistance can be ignored. Now the system is exclusively the upper tape, because it is what is being experimented on. Everything else in the universe is after the system. That includes the other tape and the stand. Initial conditions include that each tape was initially neutral and then charged, and that each tape did not have an effect on the other before they were brought together. In the actual experiment, two U tapes were created. As upper tapes, the charged tapes. One tape was then suspended and another was brought in from underneath it, and the distance between them, when one began in the float, was measured. In our case, that was 3 centimeters. Now we get to the code. In this closed-loop code, we have to define our constants first. Here we defined our constant G, M, D, Q, and here this code, what it does is it defines the electric field function for each individual point charge that we will be contributing in. This line of charge code comes later, and what it does is basically defines a line of charges where we're going to be splitting up the charges into different points. This is the actual tape creation where we see how many we're going to be creating, and this E field calculation is where actually the electric field at each point from all the other charges is calculated. So the for loop takes into account how many charges we have and how many there will be, and what the actual magnitude and direction is at each individual point. From here, we have arrow formation and printing, where we actually take all those and display them in this picture on the right-hand side, and you can see each point from left to right is being pushed away from the bottom tape. You can also see the gravitational force and the direction of the overall electric force. You can see here that the resulting magnitude of electric force is 5.13 times 10 to the negative 4 newtons. The magnitude of the gravitational force was 2.06 times 10 to the negative 3 newtons. And that the charge of tape was 1.435 times 10 to the negative 8 coulombs. There's also one calculation that we have here. In class, we derived a formula for the electric field, and we can turn that into a force equation as well. We can rearrange that into this right here, and from there we can calculate our Q from the lab to be 1.367 times 10 to the negative 8 coulombs, which is different than what was predicted in the code just before. So in conclusion, the charge of each of the tapes was, we're going to go with what the calculation says, 1.367 times 10 to the negative 8 coulombs. Well, from the lab, 1, and from the code we saw that it was 1.43 times 10 to the negative 8 coulombs. There was a slight difference there, but really that just comes from how the actual formula accounts for the distributed charges in its entirety. So instead of having, say, 50 points in the code, in the actual formula, it accounts for the integral and accounts for basically an infinite number, so it's more accurate. The magnitude of the electric force, as determined by the code, was 5.13 times 10 to the negative 4 newtons, and the gravitational force was 2.06 times 10 to the negative 3 newtons. Possible sources of error that we have are the possible differences in charge in the two tapes. There are some differences that can come with handling, and due to the quick nature of the floating, it's possible the distance between tapes when floating was slightly off. And now we come to our what if and why statements. So what happens if we had modeled each of the tapes as a single point charge? Well, it seems to stand that just as we did in lab 1, now is going to be less accurate. Why do these estimates differ? Well, just as because between the formula that comes from the derivation class in the code and between this code and last lab's code, we keep adding more and more point charges to our model. And as we get bigger and bigger and bigger, we get more accurate results as we increase the sample size of the charges, which can only be done computationally or through integrals.